Okay, here's a solution for a connected element problem. I like these because it's a fairly easy application of KVL and KCl along with active sign convention and the passive sign convention and how you interpret the use of power. And then also it reinforces this idea of conservation of energy or conservation of power. Okay, so let's get started. All right, so first of all, we're noticing that the question asks for current ID and voltage VD. So for current ID, I'm looking at a Kcl equation. All right, so I have this gold node highlighted, and I can look at sum of currents going into the node is equal to the sum of currents going out. So what I notice is that ID is coming out. So ID, I'll put that on the left side of the equation. And then I have two currents coming in. 3 amps and 4 amps are coming into the node. So 3 plus 4. And I get 7 amps for ID. All right. Then I can do a similar approach for voltage VD. I'm going to write a KVL loop. I'm going to go in this direction. And so what I'm doing with the KVL loop is I'm looking for voltage rises on one side of the equation and voltage drops on the other. All right, so as I move in this direction, I have a rise of 10, another rise of 20, a drop of 15, okay, and then finally a rise of VD. Okay, so I can solve for VD, and what I get for that is minus 15. The minus sign is not a problem. It's just the way we set up this reference, it turned out to be negative. So I'm going to show you how to handle that as we move forward. Okay, so now let's look at the power associated with each element, as in part 3. Okay, so element A. I look at element A. The voltage is 10. The current is 4. All right, so I know the power associated with A is 10 times 4, which is 40 watts. Next, I need to ask myself, what is the interpretation of power? All right, so I look at the sign convention. The current is moving in the direction of a voltage rise. Okay, so that's the active sign convention. So my interpretation is that this is supplying power. All right, do the same thing for B. B is the same thing. It's the active sign convention. Current moves in the direction of a voltage rise. 20 times 4, it's 80 watts supplied. Okay, now for C. For element C, this is different because the current is moving in the direction of a voltage drop. Okay, so that's the passive sign convention, but it's 4 amps times 15. Okay, so 4 times 15 is 60 watts. And because it's the passive sign convention, it's using power. Okay, so now to element D. Right, element D, we know the voltage value is minus 15. So let's go ahead and write that down, minus 15. All right, and then we know the current through element D is 7. Okay, so 15 times 7 is minus 105. Okay, and now we look at the sign convention, okay? Ignoring the fact that VD turns out to be negative, all right? We just look at the sign convention, okay? So current is moving in the direction of a rise. Okay, so that's the active sign convention. You see that? Here's VD. Current's moving in the direction of a rise. It's the active sign convention. So it's supplying minus 105 watts. Okay, now here's the key. supplying minus 105 watts is equivalent to using positive 105 watts. Okay, so there we go. All right, so next we have element E. All right, so we need to write a KVL loop to get the E, even though that wasn't asked for in the problem statement. To solve for the power associated with element E, you need that voltage. All right, so we write a real quick loop here. I'm going to make that in light blue. All right, here's a quick KVL loop. All right, so I have a rise of VD is equal to the drop of VE. So it turns out VE is also minus 15 volts. Okay, and then this one, we see a 3 amp, 3 amps going this way. So it's minus 15 times 3, which is minus 45 watts. But the sign convention here is current is moving in the direction of a voltage drop. All right. So the sign convention says this would be minus 45 watts used. And we know that that would be equivalent to plus 45 watts supplied. Okay, so awesome. We've gotten all the power for all the elements. All right, so next what we need to do is look at what is used and what is supplied. All right, so we see we had the 60 watts used. We had 105 watts used. And then we had, that was it, okay? 165 watts. Now we'll look at the supply side. All right, so we have 40 watts supplied plus 80 watts supplied plus 45 watts supplied. So you add those up and you get 165 watts. All right, so the power supplied is equal to the power used. And so that's what I'm looking for when I ask for you to verify that power is conserved for the circuit. All right, so I like this kind of problem. Be sure to take a look at that.